After a core collapse supernova, it's possible for that core to have stopped shrinking when it's reached about 20 kilometers in radius because of neutron degeneracy pressure. This is another type of possible stellar remnant. This is one of the things that a high-mass star is going to be able to turn into. Low-mass stars turn into white dwarfs. High-mass stars can turn into neutron stars. Now, if the core gets above around 3 solar masses, then there's no known force that's going to stop gravity crushing that core into a black hole. That's our last possibility for what stars can turn into when they die. However, we're going to first focus on neutron stars. So we mentioned previously during that core collapse supernova that the protons and electrons get squeezed together producing neutrons. Okay, then the whole thing collapses until neutron degeneracy pressure is able to fight against gravity. This is the neutron star. Now, it's so tightly packed together that it actually has a density similar to the density of the nucleus of an atom, which is the densest material that we know of. Neutron stars were actually first predicted in 1933 by the astrophysicist Fritz Zwicky, which is super fun to say. However, it was not accepted as an idea for over 30 years because nothing like that had ever been detected. People just kind of assumed that these high-mass stars would lose enough material that they would slowly turn into low-mass stars and therefore end up as white dwarfs. In the 1960s, we actually first found the evidence for a neutron star. This was actually done by a graduate student named Jocelyn Bell using a radio telescope. As she was looking through the data in the radio telescope, she found something that pulsed, meaning that it appeared to blink very, very regularly, about 30 times every second. Now, from one pulse to the next was almost exactly the same. So close that it actually was really, really weird. So she had no idea what the heck this thing could be. So she went and talked with her advisor, and her advisor had no idea of what this could be. So they both started looking through and talking to other people until it was suggested that this could possibly be a signal of what is referred to as a pulsar. A pulsar is a neutron star that appears to be blinking on and off. We've actually found some pulsars that can actually blink up to 1,000 times a second. Now we're going to talk about it in a little bit, but we believe this blinking is actually related to the rotation rate. What this means is these really, really fast pulsars that are blinking really, really quickly, those things, if they were any larger than that 20-kilometer radius that we've been talking about, the surface would actually be traveling faster than the speed of light, which you've probably heard, no matter can travel faster than the speed of light. Therefore, we actually have a very hard limit on exactly how big these millisecond pulsars are. Alright, here is our 5th lecture quiz question. How do lighthouses work? A, they have giant lights that turn on and off. Or B, they have lights that point in one or two directions and spin, so they appear to turn on and off. Go ahead and think about it, and we'll discuss in just a bit. Alright, so how is it that lighthouses work? The answer is B. They have lights that point in one or two directions and rotate. And so if it's pointing at you, it looks like it's on. If it's pointing away, it looks like it's off. So the correct answer is B. Well, the reason why pulsars appear to pulse, to blink on and off, is what we refer to as the lighthouse model. We don't think that the star itself is actually turning on and off. Instead, we believe it has beams of light and the star is rotating, just like with a lighthouse. So if the beam of light is pointing at us, we see it as on. If it's pointing away, we see it as off. Now, what causes these beams is actually conservation of energy and conservation of angular momentum. Due to conservation of angular momentum, as this object is collapsing, it's going to spin faster. Remember, our go-to example for this is always the figure skater. When she starts to rotate and her arms are out wide, she's spinning slowly, but as she draws her arms in, she speeds up. So these stars, they started out at around the size of the Earth, rotating pretty quickly. And then, in the blink of an eye, they shrink down to just 20 kilometers across, about the size of a city, which means they're going to be spinning like mad, like up to 1,000 times a second. Okay, so that's why they're spinning so quickly. As they collapse, we also have to worry about conservation of energy. So as it collapses, this conservation of energy is going to intensify the magnetic field that it already had. Okay, in a similar way that as it shrinks, the rotation rate speeds up. As it shrinks, the magnetic field has to increase. The magnetic field becomes so great that energy, radiation, can only escape from the north and south magnetic poles. Now, the north and south magnetic poles don't actually have to line up with the spin axis. So, for example, with the Earth's north magnetic pole is about 12 degrees away from true north, from the exact north pole of the Earth. The same thing can happen with a neutron star. So what this means is as it spins around, this beam will actually sweep out a cone in space. And if we're in line of that beam, then we see it as on. If we're not in line of the beam, then we see it as off. Now, we've mentioned previously that we like to use all different types of light to figure out as much as we can about what's going on. So we have launched X-ray telescopes into orbit around the Earth. Remember, we do not detect X-rays from space down at the ground. They have to be in orbit. Well, one of the things that these X-ray observatories discovered were X-ray sources that had a very regular pulse, very similar to what we saw with pulsars. The problem is that pulsars give off light in the radio and sometimes in the visible spectrum. We don't expect them to have a high enough temperature or a high enough energy to be giving off X-rays. And yet we had these sources that had a very nice regular repeating pattern of X-rays. So how could this happen? Well, one thing that we noticed is that these pulses would increase in intensity and decrease in intensity. So in this graph, up and down, we're looking at the X-ray intensity, and along the bottom, we're looking at time. So we'd have an increase of intensity of the pulse and then a decrease of intensity in the pulse. As we pinpointed where these things were in space, we often found some kind of star, some kind of giant star. As we studied this star based off of its Doppler shift, it became apparent that it had to be part of a binary pair. So what we believe is going on is that we have a giant in a period of mass transfer onto a neutron star. As this happens, this material, as it falls onto the neutron star, will actually reach up to half the speed of light before crashing into the surface. When it does crash into the surface, that's going to heat up the surface of the neutron star to around 100 million Kelvin, which is hot enough for it to then emit X-rays. So a pulsating X-ray source is the same idea as a pulsar. It's just that it's become superheated to the point it is now giving off X-rays because of this mass transfer from a companion. Now, the reason why we see the pulses get brighter and fainter in time is because of eclipses. As the pulsar goes behind the companion, those X-rays are going to be blocked from view until they come back out on the other side. Now, we actually see a similar thing with a nova, but in the X-rays. This is what we refer to as an X-ray burster, okay, because we get a sudden burst of X-rays. So in this graph, up and down, we're looking at the X-ray intensity, and then along the bottom we're looking at time, although notice we're looking in seconds in this case. So what will happen is we get a sudden flare of X-rays, and then it'll fade out and go back to normal. Now what's going on is we have a giant that is losing material onto a neutron star. As that hydrogen is falling onto the neutron star, it actually gets compressed enough that it automatically fuses into helium. So that means that we get a layer of helium building up on the surface of the neutron star. Now, once there's enough helium, it's going to compress and heat up enough that it's going to reach the pressure and temperature necessary to have a sudden burst of helium fusion. Helium fusion happens at such a high temperature that it's going to give off primarily X-rays. So this burst of helium fusion creates the X-ray burst that we see from these stars. Now, we've already mentioned that there's a limit to electron degeneracy pressure. That's at 1.4 solar mass, also known as the Chandrasekhar limit. Now, we know that there's going to be a similar limit to neutron degeneracy pressure, where neutrons are pushing out against the crush of gravity. We don't know exactly what that limit is because we don't fully understand the nature of neutron degenerate matter, but we know it's around 3 solar masses. The current estimates are anywhere between 2.7 and 3 times the mass of the Sun. Once something that is only held up because of neutron degeneracy pressure gets over this limit, somewhere between 2.7 and 3 solar masses, then there is no known force that can stop the crush of gravity. Gravity beats all, which collapses all that material down to a single point. This then forms a black hole, which we're going to spend an entire module talking about next time. So you're going to have to wait a little bit, but we will get into some good detail on black holes.